Today we begin a new topic. Hello, hello. Okay. New topic is regression and regression analysis. We're going to have it for about 2 weeks. This is a very long 70 slides, so there's no chance of getting it one time. So I'll be shooting today for hopefully between 30 and 40 slides. In other words, to do about half, and next time about half. Regression will be for the exercises and the quiz after the midterm, and will not be included in the midterm. So what we'll be doing now is do the lectures before the midterm, then exercises after midterm, and then the quiz after the exercises on regression on. So regression also has something with trend lines. Let's see what it's all about. So when there is some kind of an economic development, you want to see if there is a trend line. If the trend is going up, or if the trend is going down, or if the trend is flat. Trend could be rising real estate prices. For example, prices in real estate in Cambodia, especially in Phnom Penh, rise really fast to say that there is a real estate bubble here in Phnom Penh. Okay? You want to see if, let's say, obesity, the percentage of people over time, is it going up, 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 or stays flat? Or, again, blood pressure, or the overall economy. So, every quarter you can see what the economy is doing, and we'll take a look if there's a trend line and what the trend line is. You can also draw a plot, you can draw a picture, you can draw what we call a scatter chart. We've already done this before, we'll be doing a lot more during the exercises. When we do a regression analysis, we call these predictive analytical models. You may use a simple linear function. You may use logarithmic function, polynomial of second order, polynomial of third order, power, exponential, and so on. This is for Excel. We're going to be using other software, so we don't need to do the trend line tool over here. When you run a model, and we usually will be running, which is the main tool, a regression model, there is a measure that tells you the overall performance of the model. That measure is the R squared. It functions as a sort of a correlation. How well the independent variables explain the dependent variables. It is a measure of the fit, and it basically measures the percentage of the variation in the independent variable explained by the dependent variables. The two of you on the back, warning, okay? Next time out, okay? So, the first thing to do is you just look at a picture. It's always nice to see what the picture looks like. It's going to give you a good idea about what you might have to be doing. The relationship may be like a U, okay? So it may be non-linear. The relationship may be a curve, okay? You want to see the relationship with your eyes, and then based on the picture, decide what will be a good function. Well, give them over there the attendance sheet on the other end. So here, it seems that the relationship is overall linear and negative. Negative means that the slope is down. Positive means that the slope is up. And if we get the data when the exercises, that's going to be after the midterm, okay? You will, when you get the data, you should be able to draw this chart, and based on the chart, to draw this particular, either a trend line, we call it properly regression line, okay? Now, they give you another example, predicting crude oil prices. It's a little difficult, it's a little trickier to predict. It seems that for a while, it's relatively horizontal, meaning the trend line is flat, we say, and then it's a little bit rising. Or we may say that the trend line goes a little bit like this and then begins to curve up for a while. So it may be what's called curvilinear, coming at the very end of the lecture, probably next time. So when you use particular data, you may try to fit an exponential function, and this is what the exponential function looks like. You may try to fit in a logarithmic function or polynomial function. This is a second degree, which will include a square. Polynomial of third degree, which will include a cube and a square, and maybe a power function. And you may try some of these, but it's better if you just look with your eyes and see, oh, this function seems to be better. Now, when you do the regression, or when you do the fits, you will actually look at the R squares. And you see, oh, this R square is only 66 or 66%. 66% the variation is explained. Here, 32, obviously the logarithmic is not a very good fit. This at 90 polynomial is a very good fit. And here, the polynomial of third degree appears to be even better. Now, what's important to understand, and that will be coming many times later on, is that by adding more variables, you will be always improving the R squared. So the trick is when you add a variable to improve the R squared a lot, not just a little. So example, from the linear model, well, where's the linear? You improve to 90. So if you improve from 50 to 90, that's a huge improvement. If you improve from 60 to 90, that again is a huge improvement. If you improve from 90 to 92, it's probably not a major improvement. And there are ways to see later on. And now the last power model we see is very poor, only 40%, 39.7%. So they give you here a third line order. The third line order, I'm going back, will be this particular with x3, x2, and x. When you look at the picture, you see this is the fit. It gives you a relatively flat trend, and then it begins to accelerate on the way up. And it provides a relatively close fit. Close means that the difference between the fitted value and the actual value is not too large. It's fairly closely tracked. So, what you should always remember when you do polynomials and add extra variable, x squared, x third, and x to the fourth power, is that the R square will always improve. That's a property of the mathematics. Every time you add an extra variable, there will be always an improvement in R squared. So the tricky question is the improvement significant or minor? What you want to do is have a lot of extra improvement. That girl there, the toy. Leave the toy on the first desk. Yeah, that's you. Just leave the toy, yeah. The toy in your hand. The phone. Yes. Yes, just leave the phone up there so I can watch the phone. Yes, please, thank you. Thank you. All right. I can see the phone. I feel comfortable when I'm watching your phone, okay? And you'll feel more comfortable when watching me, right? Not the phone, okay? You can do it after class. In about 30 minutes, you can do it. Okay. So, every time you add an extra variable, you will be improving the question just a little bit or a lot, okay? When you add more and more variables, higher polynomials, they can become zigzag. You don't want to have too much of a zigzag. You want to have a relatively smooth curve. So probably high order polynomial, 4, 5, 6 degrees, will probably not be very, very good. But again, you gotta look at the data and see what the data actually looks like. You need to use intuition, okay? And that's exactly what they say. Use your time. That's the same as intuition to make a good judgment. In other words, this part of regression or statistics is as much science as it is art. You need to do a lot of exercises and a lot of practice to get an intuition for what might work, what might not work. Or if you try to say, oh no, this is not working. So intuition, number one, is you experiment. You will have to experiment and you see, well, let me try this, you see the result. Oh, let me try that, see the result, and then you get to judge. So this is where students get confused when they say, well, give me the best one or give me the perfect one. And the short answer is there is not always the best, there is not always the perfect, there's not always the right one, but you have to experiment and get to something that's close to the what we might consider the best one. So it's called trial and error. You try, maybe it works better, then you try again, maybe it's worse, maybe you improve, maybe you not improve, maybe you have to add a variable, maybe you have to remove it, or maybe you have to remove one variable, then you add another variable. This is known and should be coming as stepwise regression. Stepwise regression will basically mean when you have 3, 4, 5 variables, maybe you start out with all of them, then you drop one variable, then you drop the second variable, maybe you have to add the first variable, maybe drop the third one. So you keep adding and dropping, and here's the key. One variable at a time until you get something that looks fairly decent. All right, back to the slides. So, regression analysis is a tool for building mathematical and statistical models. You already studied regression, right? In your basic statistics course. So, here the idea is, again, I will not be teaching too much theory. The idea is that you'll be spending a lot more, twice more time in the lab trying to practice and exercise. Okay, simple regression model involves only one independent variable, so we have one dependent and one independent. In a multiple regression, it involves one independent and two or more, one dependent and two or more independent variables. So, simple linear regression, you'll have to see, again, the picture. What does it look like? Does it look like linear? Does it look a little bit like a curve? Sometimes we call this, it should be coming probably in a couple of slides, curvilinear. So it's not exactly a curve, we call it curvilinear. So it's got a nice, smooth curve. And sometimes the picture tells you, well, there's no real relationship. Maybe there is, maybe it looks like this a little bit, but maybe there isn't. Okay? So if these were a little narrower, probably there will be a positive relationship. Again, you gotta see with your eyes and get an intuition. Example. Well, there it is. I think we actually did in the lab this with the housing prices. And you actually had to compute the square feet, the market value, and you actually had to calculate the z-scores, and then actually get to see, well, this is what the data fit looks like. Just by inspection by eye, there is no regression line, but if there is, it will look like this. And there's that particular point right there. You zoom in and nice, or not zoom in and nice. All right, gotta train him. So you zoom in nice here. So you see all of these, and this is an outlier. When you run the z-score, it's probably gonna be more than 2 sigmas, probably 3 sigmas. A sigma, z-score will be a sigma, so it's going to be +2, +3, +4, maybe 3, maybe 4 when you run. And then the bigger question is the following. When you have an outlier, what to do about it? You have 2 things. Maybe you include it in the data, or maybe that one particular outlier you filter it off. When you say filter off, it will not be used to calculate the relationship. That's the one thing. The other thing which makes statistics more complicated and difficult is actually that it's not statistics at all. You will have to ask the question, why there's an outlier? What is causing the outlier? Why is this house on average $40,000 more than the others? What's special about this house? It may have a swimming pool, right? It may have a triple garage, right? There are families that will have 3 or 4 cars, and they're desperate to have a triple or 4 garage, 3 garages. So they'll pay a lot of extra for the garages, or the swimming pool, or whatever other facility it might have. It might have a little forest, it might have a fitness area, whatever it might be. So, a business, common business sense is to investigate what is causing the outlier, just look at the reality, and then to decide do you include it or exclude it. And you may draw a lot of different lines. The question is, how do we have a best fit? What is the definition? Is this curve, which is A curve, better fitting, or is this B curve better fitting? Well, to the eye, A looks a lot better fitting. But if you include the outlier, statistically, B would be better fitting. And again, which makes more common sense by just using your eyes? Obviously, A is better. Do they say, oh yeah, line A is better fit to the data? Okay, they even give it to you. All right, so best fit regression. Let's keep cruising. So you can use Excel. We'll try to use SPSS or PSPP for this. You run the regression. Basically, in the exercise, you got the data. You should be somehow able to get this regression line or this model. You should be able to get the same model. And again, you may have to remove the data. You may have to have it. You'll see how you're going to get there. This is called, again, trial and error. You'll have to experiment. You're not going to get it always right from the first time. That's nothing to do with you. This has to do with the nature of the process. even the best statisticians in the world with 20 or 30 years of experience will have to go through a lot of experimentation. We call it trial and error. They'll have to go backward and forward, sometimes many times, before they get to what they think seems to be the most appropriate. That's the correct word in English, is to get an appropriate model. You will not always know what's the best, okay? There's no such thing as best. There's no such thing as perfect. But you want to get an appropriate model. An appropriate model will be simply defined as just good enough. Again, you don't need perfect results always. Probably you're going to be using sample. And when a sample of 50 observations out of 5 million, you will have a lot of distortions in the data based on the sample. So even if you get the perfect model, just your sample will be screwing or biasing the result. So we don't need to shoot for perfection. Just good enough is good enough. Let's see. So the most common method to get a regression, to define a best fit, is known as least squares. And least squares simply tries to minimize the differences between the deviations. There's a little picture over here. This is the one deviation. We call this an error. And this is another deviation. It's called an error. So you take the squares and you sum them. And you want to be the minimum of those squared errors. Minimum will mean that the line will fit as closely to the data as possible. And when you use the squares, some nice mathematical properties appear out there. So these we call errors. These we call errors. E1 and E2. And the least squares is usually calculated with what looks like a complicated formula, but it's relatively simple, relatively straightforward, and for you it's all done in a 1/10 of a second in the software, both Excel and the PSPP software. So we're not going to do the using Excel functions. We're going to do the PSPP. Of course, it's going to calculate everything for you. So you get the data. You will try in the lab after the midterm to see if you can get these results. Okay, you get the results. So you're going to try to get. And if your results will be exactly like theirs or close to theirs, or they're going to be very different. And they show you how to use Excel. I mean, you can play with it, but you probably don't have to, at least for this course here. And this is what the results will look like. Let's spend a little bit of time over here. First, you will have what's known as multiple R. Multiple R is associated with regressions. When you have a simple regression, you will have multiple R, that's the R squared. And with a multiple regression, you'll be getting the R squared, okay? And then here's the trick. That's important to understand. It's probably going to come a few slides down the road, maybe next time, that there's R squared and adjusted R squared. And the adjusted R squared is always lower than the R squared. And the adjusted R squared is adjusted for the number of variables. So when you add a new variable, the R squared will always for sure go up. But the adjusted R squared may go up, which will make the model improving. or the adjusted R-squared may actually go down and make the model worse, okay? So the adjusted R-squared is actually the more appropriate measure to look. So you should not focus on the R-squared, but you should always focus and look the adjusted R-squared. And again, when you add an extra variable, you want to see if the R-squared jumps up a lot or a little bit. And then you want to verify if the adjusted R-squared will actually go up or it will actually go down. And there will be ANOVA. And ANOVA analysis is very similar. ANOVA analysis is very similar, and ANOVA will simply tell you, is the overall model good or not good? What is this toy? Let's take a look at the toy. Join the other toy. Okay, so ANOVA will tell you, and ANOVA is a fun finish. Well, you can resume in about 15, 20 minutes, okay? You can continue to play after. So ANOVA is an F test, and it provides an F statistic. And the F statistics has a distribution, and you will look the F test with the probability. The probability both for the exam and of course for the midterm, the probability will come as 2. Either as the prob value or as p value, or now pay attention, or as significance, because our software will usually say significance. So when the software gives you significance, it's the same as the p-value, okay? That's how the software calls it, significance. So significance, this is actually a very small number, 3.7 to the power of -8. This means that it's 0.000 with 7 zeros and then 3.7. Now, our software, we're going to give it simply as 0.000. And this means that the test is highly significant, more than 1 in 1,000. And again, if it's more than 1 in 1,000, doesn't matter, it's 1 in 10,000 or 1 in a million. It is very significant. So the F test will give you the overall information for the overall model, whether it's good or not good. And then, pay now attention to the next part, will be the T statistic. T statistic will apply to every single variable, to every single coefficient. The first one is called intercept or constant. So, the constant will have its own T statistic and its own p-value, as in significance or prob value. So here, the T statistics is 3.6. The cutoff value is about 2. So if it's over 2, is very significant. Here the p-value is 0.0006, 3 zeros and 6. This is highly significant. And here the t-stat is 6.7, very high. And the p-value is practically 0, meaning 3.7 to the power of -8. This means 0.00000070379. Okay, highly significant. So both, we call these parameters, are highly significant based on the p-value, and the overall model is also highly significant. Now let's take a look at something else. Because this particular model is a simple regression, there's only one variable, the square feet, the other one is a constant. The p-value, 3.79 to the power of minus 8, is identical to 3.79 to the minus 8 is the same as the significant f-test. So the f-test for a simple regression is the same as the t-test and the t-statistic. But when the model becomes a multiple model, maybe 2, 3, 5, 10, or 15, then if you have 10 independent variables, each independent will have a t-statistic, and then again an overall f-statistic for the whole model. And you might even, as you add or drop variables, look whether the f-statistic will also improve this f-statistic, or its probability p-value will improve or not improve. Okay, so you'll be looking at two things to see if the model improves. You'll be looking at the adjusted r-square, or you'll be looking at the overall f-value of the model. Let's see what else we got. Okay, regression. So, the regression statistics, they are explaining here what I've been doing for the last few minutes. You got the multiple r, you got the r squared, then you got the adjusted r squared, adjusted for both sample size and the number of variables, and the standard error. Okay, that's going to be coming maybe later, or not focus so much. And now comes the next part. In other words, after the midterm, for the second half of the course, for the first half, all you needed to do was basically get the data, get some results. Now we're getting to the point of interpreting the result. What the results actually mean. So up to this point is, well, try and get the result. What is the number? What is this value? What's the p-value? What's that value? What's the one mean? What's the other mean? Now we get to actually begin to think. What is the results meaning? What does it mean? Does it mean that people are getting fatter? Does it mean that they're getting sicker? Does it mean they're getting smarter or dumber or richer or poorer, right? What does it mean? Are things getting better or things getting worse over time? Or what makes some students better? What makes some students worse? Okay? Or, as we always like to test, are girls actually smarter? Right? That would be a nice test, right? Maybe, maybe not. Again, we don't know. So you want to interpret the result, and that's going to be coming after as in the second part of the course. The first part was, well, let's just learn the software, let's learn to get the data, let's learn to run and get the results. Now the next step is, what do they mean? Okay, what's the business implication? All right. So here you see the multiple r is very high, the r squared is 53, the adjusted is 52. And sometimes you may look at the standard error, that's not very interesting. Okay, the ANOVA is this. I think these are the same results, basically. So, ANOVA, I explained, is an F-test to determine the overall fitness of the whole model. Okay? And you can use the p-value, the same as significance. Let's see what they have here. So, for example, here you got the home size is not a significant value, home size is significant value. Oh, the p-value is extremely small, to the 10 minus 8, it's like 0.000. So, we reject the null hypothesis and we can conclude that home size is very significant. Of course, this makes perfect sense anywhere in the world. Bigger homes everywhere in the world by every single culture are considered to be better, and people in every culture are willing to pay more for bigger homes. So you'd expect that bigger homes would be more expensive, and the statistics shows it. Let's see what else we got. Testing hypothesis, okay. So you can also use the slope for the t-test. We already did that. The t-test, I explained what it means. Let's see if they got a multiple or a single. Again, they show you the t-statistic and the prob value. Again, I explained that same thing. You can, for each parameter, whether it's the slope or for each coefficient, you can have a confidence interval, okay? And you can create a 90% confidence interval so that you can take a look and see what the slope actually looks like. They don't have a picture, but I can draw a simple picture. And if this is the trend line, the confidence will be, maybe it's going to be a little bit steeper and maybe a little bit flatter. So the question is, confidence, is the confidence very steep and very flat, or is it relatively narrow? So how good is the estimated, the estimated slope that will be given by the confidence of the slope variable. In this particular, it's going to be B1. And you can also test whether the slope is a particular value. So kind of a one-tailed test. So you can test the slope against 0 just to check if it's significant, or you can test the slope against something else. Okay, interpreting confidence intervals, maybe we'll do them, probably we won't do them. Again, this is what it looks like. Let's see what they have. Things now get a little bit more complicated. Sometimes when you run a regression, well, most of the times, it's a good idea to take a look at the residuals. You want to look at the residuals and see whether the residuals look nice or don't look nice. And nice has a number of meanings. The residuals have to be somehow normally distributed, okay? They have to have pretty much the same variance. Probably slides will be coming later. Yes. So, overall, they have to be linear, okay? So you cannot have the residuals looking in a funnel that opens up or that closes, okay? The residuals should have a normal distribution around the mean, okay? That's also very important. The homoscedasticity is that the variance of the residuals must be constant. So when you plot the residuals, they don't look like a funnel. So these are the residuals over here, and it's an opening funnel. So the residuals shouldn't be getting bigger and bigger with X. So you don't want to have the residual. Now, maybe I need to explain. Residual is simply the error of the fit. It's the difference between the observed value and the fitted value. So that's homoscedasticity. Homoscedasticity means that it is a channel, okay? Parallel channel. And the opposite is called heteroscedasticity, which means it's a funnel. If it's a funnel, usually shows you a problem. And if it's a channel, is relatively okay. And finally, they must be independent. So, independence, you look a picture by the residuals staying either too much positive or staying too much negative. They should be zigzagging quite randomly. let's see what they have. Linear trend in scatter plot. There is no particular pattern. So there is no quite particular pattern. Again, you can see one outlier. You see the outlier by a major residual. Basically, this tells you, hey, this particular house is $30,000 more than what we would expect. And the question is, what's causing it, okay? And yeah, they overall look okay. Now, when you actually get the residuals, maybe you can ask the software to draw the residuals, and then you ask the software to make for you a histogram. Does the histogram look like a bell shape or not? And this looks fairly bell-shaped. Again, not perfect, but good enough. Let's see, homoscedasticity. Well, they are relatively parallel. You don't really see a wide opening funnel. You have one outlier. Again, you need to investigate what the problem is there. You also need to look at independence. There are some tests. Probably will do, probably won't do. We'll see what the exercises want us to do. Multiple regression. I think right now is 36 out of 72 slides. We're exactly in the middle, okay? So we're gonna finish up to here. This means cameraman, your bonus point, and